Yeah, good evening, everyone. I welcome you all to the week 11 live session on NPTEL Bioinformatics Algorithms and Applications course. So this would be the last problem solving session. The 12th session will be an doubt clearing or overview session. So coming to know about the session, so here I'll be discussing about the summary of the different machine learning techniques and how these techniques are validated, developed, and everything. Followed by this, for each technique, we'll be doing some numerical as well as some theory questions, which helps us in our understanding. Followed by that, I'll take any questions from you. Okay, to start with the machine learning. So, talking about machine learning is based on the idea that computers can learn from data and identify patterns on their own without being explicitly programmed. So, this without being explicitly learned is what this means. So it involves developing algorithms that can automatically improve their performance on specific tasks by learning from examples or previous past information or input information. What is difference between a traditional programming and a machine learning? So in traditional programming, a programmer writes a code that tells computer exactly what to do for a specific task. However, in machine learning, the computer learns to perform a task by analyzing and learning from the large amounts of previously present data. The machine learning algorithm can then use this learning to make these predictions or decisions on a new data. So the machine learning algorithm tries to learn from the data and then tries to predict based on its learning experience from a past data to make predictions on a new data. So the process of machine learning has shown here involves feeding large amounts of training data into an algorithm and allowing the algorithm to learn from that data. And the algorithm, so how it learns means the algorithm looks for patterns and relationships in the data that are relevant to task. Once the algorithm has learned from the data, it can be used to make predictions or decisions on the new data. For example, in image recognition, a machine learning algorithm can be trained on large data sets of images labeled with different categories such as cat or dog. The algorithm learns to identify the features and patterns that distinguish cats from dogs. So once the algorithm has learned from this data, it can then be used to identify whether a new image contains a cat or a dog. So to summarize the introduction of this, machine learning is a powerful tool that enables computers to learn from data and make predictions or decisions based on that learning. It has many applications in areas such as natural language processing, image recognition, speech recognition, and autonomous vehicles, among others. So next, to move forward, we'll be discussing about types of machine learning techniques available. So mainly there are three types of machine learning. So if we classify, machine learning falls into the three classes. One is supervised learning, reinforced learning, and unsupervised learning. In supervised learning, the algorithm is trained on a labeled data. Here, labeled data means that the data has a known output or a target variable. So in this supervised learning algorithms, the algorithms learn to predict the output for a new input data based on the patterns it learned during the training. So in supervised learning, we give a set of features and the output variable, and then if you give a new set of features, then it will predict the output variable. In unsupervised learning, the algorithm is trained on the unlabeled data, which means the data has no output or target variable. Here, the algorithm learns to find patterns and relationships in the data, such as clustering or dimensionality reduction. Next is a reinforcement learning. In reinforcement learning, the algorithm learns to make decisions by interacting with an environment or receiving feedback in the form of an rewards or punishments. The algorithm learns to maximize the cumulative reward over time by taking actions that lead to positive outcomes. Talking about applications, machine learning has wide range of applications across various industries, including in healthcare industries where it is used for a disease diagnosis or prediction, or in finance where it is used for fraud detection, risk assessment, and other things, in marketing or in manufacturing, transporting, and many other things. So, overall, machine learning has the potential to revolutionize many industries and improve our daily lives in numerous ways. So, here I would like to discuss, before moving on to other, the brief process how a machine learning model or algorithm is developed. So the process of developing can be broken down into several key steps, which are as shown here. First is data collection. The first step in machine learning process or development is to collect and pre-process the data. This involves identifying data sources, collecting data, and cleaning and transforming the data, and splitting the data into train, validation, and testing steps. Data pre-processing also involves feature extraction and feature selection. So which includes selecting and transforming the relevant features in the data that will be used by the machine learning algorithms to make further predictions. The next step is to select an appropriate machine learning algorithm that is best suited for the task. There are many types of machine learning algorithms, including supervised, unsupervised, or reinforcement. There are many algorithms developed in these three categories. The choice of algorithm depends on the type of problem being solved, the type and size of data, and the desired output. Once an appropriate algorithm is chosen, the next step is to train the model using training data. During training, the algorithm learns to identify patterns and relationships in the data that are relevant to the problem being solved. The performance of the model is evaluated on the validation set to ensure that the model is generalizing well to a new data. So how can we confirm a model is generalized? So we develop a model on a training data set and we validate the model using a test data set, which is a new data set, which these data points won't include in the training. So if the performance is very good on the test data set, so we conclude that our model has been generalized very well. After model is trained, it is evaluated on the testing set to assess its performance. If model is not performing well, then it may need to be fine-tuned by adjusting its parameters or by changing the algorithm. So this fine-tuning is called as hyperparameter tuning. So once we have a very good model trained and evaluated, it can be used to make predictions or decisions on a new data. So here, briefly talking, the output of the model can be in the form of classification, where the model predicts the class of an input, or a regression, where the model predicts the continuous value. Overall, the process of machine learning involves several key steps, including data collection and pre-processing, choosing an appropriate algorithm, training the model, evaluating and tuning the model, using the model for predictions or decisions, and monitoring and updating the model over time. Next, talking about these algorithms more detailedly, just give me a second. Now, starting with the supervised learning. Supervised learning is a type of machine learning where the algorithms learn from the labeled data, which means that the data is already labeled with the correct output. The goal of supervised learning is to learn a mapping from inputs to output. There are two main types of supervised learning. a regression problem and a classification problem. In regression, the goal is to predict a continuous output such as the price of a house given its features such as locality, the type of house, number of rooms available. In classification, the goal is to predict a categorical output such as whether an email is spam or not. So given the metadata or the content of the email, we will ask, we would like to classify it as spam or not. Next is unsupervised. Unsupervised learning is a type of machine learning where the algorithms learn from the unlabeled data, which means that your data is not labeled with any output. So how this works? So it will read the input data and try to make it into cluster or group the data where the similar ones are grouped together and dissimilar ones are grouped separately. Now this is kind of a clustering. So the goal of unsupervised learning is to learn the underlying structure of the data. So there are two main types of unsupervised learning: cluster and dimensionality reduction. Next is the reinforcement learning. Reinforcement learning is a type of a machine learning where the algorithm learns from interactions with an environment to maximize a reward signal. So example of reinforcement learning application include game playing, robotics, and autonomous driving. So the three main types of machine learning are supervised, unsupervised, and reinforcement learning. Each type of learning has its own set of algorithms and applications, which we'll discuss in some time. And choosing the appropriate type of learning depends on the problem being solved and type of the data available. So before moving into the next steps, I would like to discuss what is trained set and a test set in a machine learning model. So as I mentioned before also in machine learning, it is important to evaluate the performance of a model on a data it has not seen during the training. So the process of splitting data into two sets, one for training the model and other for testing the model performance, is called train test split. The train test split is typically performed by randomly dividing the data set into two subsets. So one subset is called as a training set and other subset is called as a test set. Here, the training set is used to train the model while the testing set is used to evaluate the performance of the model. So here, testing set will be new and unseen data. Here, okay. Now it is clear that we need to have two training and test. So, but in what ratio we have to, whether it is 50-50% or 60-40 or 70-30. So the ratio of size of training set to the size of testing set can vary depending on the size of the data set and complexity of the model. In general, 80 is to 20 or 70 is to 30 split is used. The train test split is important because it allows us to estimate how well the model will perform on new data. If we train and test model on the same data, it will perform well on training data, but it may not generalize well to the new data. So the steps involved is this. This train test split looks simple, but it is important technique in machine learning. It is essential to ensure that the model is able to generalize well to new unseen data and to avoid overfitting of the model to the training data. So before moving, I have some questions. So we'll start with the first one. Which type of machine learning technique is used when data set is not labeled? These answers can be provided using the chat box. So which type of machine learning technique we'll be using if the data is not labeled? Whether we go for supervised learning, unsupervised learning, semi-supervised learning, or a reinforcement learning. No answers yet. Yes, it is an unsupervised learning. So, unsupervised learning includes algorithms like clustering and dimensionality reduction, where this try to identify the features among the input data and try to cluster them or group them. So, the next question is, which machine learning technique is used when dataset has both labeled and unlabeled data? Yeah, this is the one I didn't discuss, but from the options, I think one can answer this. Okay, I got the answer of reinforcement learning, but it is a semi-supervised learning. Why not reinforcement learning? Because this is a reinforcement learning differs based on how the model is developed and how we penalize or how we recognize a signal in development. So semi-supervised has labeled data and it tries to predict the missing features and then try to predict the labeled output is how it works. This semi-supervised discussion learning I discussed in the last class. Moving on to the third one, which machine learning technique is used to perform text classification task? Yeah, yeah, it is an supervised learning. Now, next, the fourth one is, what is the purpose of splitting a data set into training and test set? So, this question states why we have to do this train test split, because we wanted to evaluate the model's performance on a data that it has not seen before. So this will help us to understand how generalized or whether our model is generalized or applicable on general or not. Next is, what is the recommended ratio of splitting the data set into training and testing sets? So we are in the fifth one. So which talks about what is the recommended ratio of doing. Yeah, the ratio will be depends on size and complexity of the data set. But in general, having a larger data sets, we go for 70 is to 20 or 80 is to 20. Then this is the last one. So what is the difference between the training set and the testing set? Yes, here the answer will be B. Please give me a minute. I would like to connect back to my network. There is a network interruption. I'll be doing it in a minute. Meanwhile, you can raise any questions that you have in this learning. Yeah, sorry for the interruption. Let me share my screen again. Yeah, here we use a training set for training the model, and testing set is used to evaluate the model's performance. Moving forward, we are talking about the first type of problem is a classification problem. So classification is a type of supervised learning in which the goal is to assign each data point to a specific class or category. Here the input data is labeled with a set of predefined classes and algorithm. So this algorithm learns to predict the correct class for the new and unseen data based on the patterns learned from the labeled data. There are two main types of classification problems: binary classification and a multi-class classification. Binary classification is a type of classification problem where there are only two possible output classes. For example, classifying whether an email is spam or not, or telling whether a patient has a disease or not. There are various algorithms used in binary classification, including logistic regression, support vector machines, and decision trees. So these algorithms are trained on labeled data to learn the patterns that differentiate between the two classes. Once trained, the model can then make predictions on new and unseen data. Next is the multi-class classification, which is a classification problem where are three or more possible output classes could be present. For example, classifying different types of animals such as cats, dogs, and birds. There are various algorithms used in multi-class classification. Again, there are some common ones also. Here, the only difference is neural networks will also be used. These algorithms again are trained on the label data to learn the patterns that differentiate between the different classes. Once trained, the model can make predictions on new and unseen data. In the both binary and the multi-class classification problems, the accuracy of the model is measured by its ability to correctly classify the input data. Common evaluation metrics used in classification are accuracy, precision, recall, and F1 score. So overall, classification is an important problem in machine learning with many real-world applications such as spam detection, sentiment analysis, and image recognition. Talking about the data set. In machine learning, a classification problem dataset is a collection of data that is labeled with a predefined classes or categories. The dataset is used to train a classification model to learn the patterns that differentiate between different classes so that the model can accurately predict the class of new data. So a classification dataset typically consists of two main components, the input features and the target output. The input features are the characteristics or attributes of each data point, while the target output is the class or category label assigned to each data point. For example, in a dataset used for binary classification, to distinguish between spam and non-spam emails, the input features may include the text of the email, the sender's address, and the time of the day the email was sent. And the target output would be a binary, that is a 0 or 1, true or false, spam or not, yes or no, indicating whether the email is spam or not. So these classification datasets can be created in various ways, such as manually by labeling data using web scraping to collect manual labeling of the data, or using web scraping to collect data, or using pre-existing datasets available in public repositories. These datasets may be cleaned and pre-processed to remove missing values or relevant features before being used for training the model. It is important to choose a high quality and a representative dataset for training and classification model to ensure that the model can accurately generalize to new and unseen data. Here, the size and quality of the dataset can significantly impact the performance of classification model. So, in a classification problem, feature extraction and selection are crucial steps in the process of preparing data for training and machine learning model. Feature extraction involves converting raw data into set of features or attributes that can be used to train the model, while feature selection is the process of identifying and selecting the most relevant or important features to improve the accuracy or efficiency of the model predictions. Talking about feature extraction, it is the process of transforming a raw data into set of features or attributes that can be used for training and machine learning model. The goal of this feature extraction is to represent the data in a way that captures the most important characteristics or patterns that are relevant for the task. Next is the feature selection, where it is the process of selecting the most relevant features from a larger set of features to improve the accuracy and efficiency of the machine learning model. The goal of feature selection is to reduce the dimensionality of the data while preserving the important information. So overall, the feature extraction and selection are crucial steps in the process of preparing data for training a machine learning model. The selection of relevant features can significantly improve the accuracy and efficiency of the model while also reducing the complexity of the problem. Next, I'd like to discuss about several types of classification algorithms in machine learning, along with their little information about their mathematical background. So, starting with the logistic regression. So, this is a linear classification algorithm that uses a logistic function to predict the probability of a binary outcome. So, it models the relationship between the input features and the binary target variable by estimating the probability of a positive class as a function of input features. So here the probability of class A or probability of class B of any class of a binary class, any one class of a binary class is calculated as a function of input features. So here logistic regression will use a cost function called negative log likelihood, which is minimized during the training. Coming to its mathematical background, the logistic function used in logistic regression is a sigmoid function that maps a real valued input to any value in between 0 and 1. We also know the probability ranges between 0 and 1 also. So the model parameters are estimated using maximum likelihood estimation, which involves finding a set of parameters that maximizes the likelihood of an observed data. Next is a Naive Bayes. This is again a probability based classification algorithm which is based on Bayes theorem. It assumes that input features are conditionally independent given the class label, which is a naive assumption but simplifies the computation of probabilities. So in this algorithm calculates the conditional probability of the input feature given each class label and then uses Bayes theorem to compute the posterior probability of each class. So we all know this Naive Bayes theorem tells about the joint probability distribution of input features and class labels to compute the posterior probability of each class given the input features. Next is the decision trees. So these are non-parametric classification algorithms. So that partitions the input space into set of rectangles or boxes and each of which corresponds to a class label. And next is the random forest. Random forest is an ensemble classification algorithm. So here ensemble means collection. So this is random forest is a collection of individual decision trees which are trained individually to improve the accuracy and robustness of the model. So these understanding the mathematical principles behind these algorithms is essential for selecting the appropriate algorithm for a given problem and optimizing its performance. Now training is done. So these models can be used for training. But how we are validating? So first I'll start talking with a confusion matrix, which is a table that is often used to evaluate the performance of a classification model. It is also known as an error matrix. It summarizes the predicted and actual values of a classification problem. So the confusion matrix has four metrics: true positives. So these are number of instances that were correctly predicted as positive by the model and actually also they are positive. Next is false positives. The number of instances that are predicted positive by the model but they are actually negative in reality. Next is false negatives. The number of instances that were predicted negative by the model but were actually positive in reality. Next is true negatives, where number of instances that were correctly predicted as negative by the model. So here I have shown the confusion matrix, which is an 2 by 2 matrix. Here the rows represents actual and the columns represent the predicted ones, or it could be either way. So given a confusion matrix here, uh, can you answer the four questions? Can you mention number of true positives, number of false positives, number of false negatives, and number of true negatives. Given a confusion matrix telling about spam and not spam. Confusion matrix also provides valuable information into the performance of a classification model. So it can be used to calculate various performance metrics such as accuracy, precision, recall, and other scores, which I'll be discussing in the next slide once we solve this problem and move forward. Yeah, any other answers apart from ones that have been mentioned? So here TP stands for true positives, where the actual and predicted value has to be the same, and that has to be positive. So considering here spam as a positive class. Yeah, the answers that are mentioned in the chat are correct. So true positives are 50. So spam detection cell we can see 50. False positives are 10. So false positives will be the actual value should be not spam, but the predicted value should be a spam. So it is uh, this is second row first value which is 10, and the false negative will be actual value has to be positive and the predicted value has to be negative. So not spam. These are also 10. Finally, true negatives where actual and predicted are not spam. 30 entries. Moving forward for different metrics to evaluate the performance of a classification model. Yeah, starting with the accuracy. So accuracy is the most basic and intuitive metric for classification. It measures the proportion of correctly classified instances among all the instances in the dataset. So accuracy is measured by TP plus TN divided by TP plus TN plus FP plus FN. There are some other metrics such as precision. So precision measures the proportion of true positives among the all positive instances. It is used when the goal is to minimize false positive. The precision is calculated by number of true positives divided by sum of true positives plus false positives. Next is recall, or it is also called as sensitivity, which measures the proportion of true positives among the all positive instances. It is used when the goal is to minimize false negatives. Here, the sensitivity is calculated as number of true positives divided by sum of true positives plus false negatives. Next, we have specificity, and there are some other metrics such as ROC curve, which stands for receiver operating characteristic curve. So, which is a graphical representation of true positive rate against the false positive rate for different classification thresholds. It is used to evaluate the trade-off between the sensitivity and specificity of a binary classifier. Here, area under the curve is the important value, AOC or AUC, sorry. AUC is a scalar value that represents the area under the ROC curve. It provides the measure of overall performance of a classifier. Overall, choosing the appropriate classification validation metrics depends on the specific problem and the desired trade-off between the precision and recall. It is important to consider the strengths and limitations of each metric to evaluate the performance of the model using multiple metrics. So till here we are done with the classification. Here we have some questions starting with the first one. So in a binary classification model, we have 90 true positives, 10 false positives, 5 false negatives, and 895 true negatives. So can you calculate the model's accuracy? So I know this is a numerical problem. I'll wait for some time. And also, you guys can take note of this image, take a screenshot or a image photo of this image, which helps you in solving. So here accuracy is given by sum of true positives and true negatives divided by sum of true positive, true negative, false positive and false negative. Here this is the first one we are solving. Yeah, it's 0.98 is the answer that I got. Yeah, it is the right one. So where as I mentioned, accuracy is sum of correctly predicted instances by all the instances. So true positives and true negatives are correctly predicted ones. So 90 plus 895 divided by sum of all the instances. So which gives rise to 0.98. Moving forward to the second one, in a multi-class classification model that has correctly classified has 70 samples out of 100 samples, what is the model accuracy? So to answer this, think what does correctly classified instances stand for? accuracy can also be defined as number of correctly classified instances by total samples. So it's zero point 0.7 because 70 are the correctly classified ones divided by 100. Yeah. Moving forward for the third one. So which of the following techniques can be used to prevent overfitting in classification models? We are on to a third question. Which of the following techniques can be used to prevent overfitting in classification models? Any other answers apart from C? Okay. Yeah. Here, all of the above. Regularization, cross-validation, and feature selection. All these techniques are different ways of for assessing the overfitting of a model. So the fourth one, which of the following is a disadvantage of a decision tree? So we discussed a decision tree to be an uh, non-parametrical method of doing a classification, solving a classification problem. Yeah. I mentioned the decision trees can handle the binary as well as the multi-class, multi-binary, multi-class problems as well. Here the problem is decision trees are trying to overfit more because of their calculation metrics or performance metrics are very not very generalized. When you see a decision tree and a random forest performance, you see they'll have very high performance on the training set, but when you give an new or unknown test set, the performance declines very high. Okay, moving forward with the regression. So regression is a type of supervised learning problem where the goal is to predict continuous output based on a set of input features. In regression, the algorithm learns from the labeled data to predict the value of a dependent variable based on the values of one or more independent variables. So broadly, two types of regressions we discuss: a linear regression. A linear regression also includes MLR, multiple linear regression. Then other one is a polynomial regression. So linear regression tries to build a linear relationship between the input features and the output predicting variable. Whereas polynomial regression use a polynomial regression. So in linear regression, we only see x, y, z terms. But in polynomial regression, you see x square, y square, z square, x, y, y, z, and zx kind of combinational features you see. Talking about the data, uh, it consists of input variables and output variables, where input variables are used to predict the output variable. So here in regression problem, the input variables are called as independent variables or features, and output variable is called as dependent variable or target. Same again, this regression data can also be split into two parts: training and testing data set. And there are some data sets, examples are time series data sets, cross-sectional data sets, and panel. So in regression problem, it is important to note that there is a pre-processing step before developing a model. That is transforming, normalizing, and cleaning the data. Normalizing is converting the range of data into in between 0 and 1. So this pre-process uh, ensures that the regression model can learn from data effectively and make accurate predictions. And similarly, we have feature extraction and feature selection techniques. So the techniques here include principal component analysis. So this includes reducing the dimensionality of a data by identifying the principal component that explain the most variance in the data, that is, which can understand more error in the data. So using PCA, we'll get most important features in the data, and also it will reduce computational complexity. And next, the widely used one is correlation analysis. So this will try to identify the features that are highly correlated to the output variable. Next is regulation and recursive feature elimination, where recursive feature elimination involves recursively removing the least important features. Okay, this feature is not important, okay, I'm removing it. Overall, feature selection and feature extraction are important techniques for building effective regressive models. They help to identify the most relevant features in the data and reduce the dimensionality of the problem by making it easier for model to learn from the data and make accurate predictions. So we have talked about linear regression, multiple linear regression, then followed by polynomial regression. But coming to support vector regression, the support vector regression is a regression technique that uses support vector machines to model the relationship between the input variable and the output variable. So support vector machine or support vector regression uh, is widely used technique, so which involves constructing of an hyperplanes and support vectors to understand the data and to segregate data. And it is also important to note that it is important to evaluate the performance of each technique by using appropriate metrics such as mean square error, R square, and these metrics will also help us to compare the performance of different models developed. So coming to the validation metrics, so here I'll be discussing with this some commonly used ones. First one is mean square error. So mean square error is the average squared differences between the predicted values and the actual values of the output variable. It is widely used metric in regression and is sensitive to outliers. So these metrics has their own strengths and weaknesses. Here the formula is given where y is the actual value and y pred is the predicted value and n is the number of observations. Next is the root mean squared error, shortly known as RMSE, is the square root of mean square error and is also widely used metric in regression. So we add square root to the mean square error MSE we get RMSA. Next is mean absolute error, shortly known as MAE. MAE is the average of absolute differences between the predicted values and the actual values. Think we have a predicted value of 10 and actual value of 8. So the difference is 2. Even if it is negative, the value is 2. Because mean absolute value we take here. Next is R squared. So this measures the proportion of variance in the output variable. So this R square ranges from 0 to 1, where 0 indicates the model explains, understands none of the variance in the output variable, and 1 indicates the model explains all of the variance in the other things. And we have R square and adjusted R square, which are other metrics that uh, helps us to evaluate the models. Yeah, here are a few questions on regression. So the first one, what is the purpose of regression analysis? Yeah, any other answers on this? What is the purpose of a regression analysis? Yes, it is B. So where in a regression analysis, we try to predict the value of a dependent variable based on one or more independent variables. Second one is, what is the difference between simple linear regression and multiple linear regression? So as we discussed, simple linear regression has only one independent variable. So where it is given as y equals to f of x, whereas multiple linear regression is given as y equals to f of x1 comma x2 comma x3 comma so on. So coming to the third one, which of the following is a type of regression analysis used for predicting binary outcomes? So which is a regression technique we discussed in predicting binary outcomes in an or in a classification problem? Yeah, it is logistic regression. So now we'll be solving some basic assignment questions. So, talking about K means clustering. So, what does K stand for? Yes, K stands for number of clusters or groups. Moving on to for predicting a type of a test protein X between two groups A and B based on amino acid composition, which of the following statement is not applicable is not correct? Read the options carefully so that you can select the one which is not correct for classifying or grouping this test protein X in any of the group A and B. Yeah. So when we check with the answers, and particularly when we see with the option C, they're telling deviation between X and B is higher than A, and correlation between X and A is higher than B. So, if deviation is high with B, so it has greater chances that it could be A. And second line also tells that it has high correlation with A. So this also confirms that this mostly this X should be A, but option they have given it as B. So this is the wrong one. Now moving forward for the two more simpler ones. In a simple linear regression, what is the slope of a regression line? What does the slope tells? Okay, here the slope of a line tells change of a dependent variable for a unit change of independent variable. So how slope is calculated if y is an dependent variable and x is an independent variable? Y2 minus y1 divided by x2 minus x1 is the formula. Followed next is what is multicollinearity in multiple regression? Yeah, this is correlation between two or more independent variables or features. Moving forward for a calculation question. So given an confusion matrix, can you calculate sensitivity, specificity and accuracy? Okay, for your reference, I'm giving an formulas as well. So I'll wait for some more time for you people to solve this. Yeah, before answering this question, take care whether the row wise are predicted or the column wise are predicted, and then select false positives and false negatives. Whether rows are represented by here when you see uh, in the confusion matrix actual values are represented in columns, but in the image or in the formula table the actual are represented as a rows. So make sure this changes. let us see the answers. So the sensitivity is calculated as number of true positives divided by true positives plus false negatives. Here, true positives. Okay. Yeah, here true positives are 5. That is actually positive and predicted as positives. 5 divided by 5 plus false negatives. False negatives means actually they are positives but predicted as negatives. So actually positive predicted as negative are 0. So 5 divided by 5. Yeah, your answers are correct. Next, specificity. Specificity is number of true negatives divided by true negatives plus false positives. Here, true negatives are which are actually negative and predicted as negative. So it is 1 and divided by 1 plus false negatives which are actually positive. Oh, no, sorry, false positives which are actually negative but predicted as positive. That is 4. So 1 divided by 1 plus 4 is 1 by 5.2. Then accuracy is number of correctly predicted ones. So number of true positives, true negatives divided by total number. That is 1 plus 5 divided by 1 plus 5 plus 4, 10. So 6 divided by 10 is 0.6. I hope everybody is clear in this. So moving on to the next one. So given specificity of a classification method as 0.75, can you predict the false positive rate? So here are the formulas for them. So when you have a specificity value, so can we convert somehow or calculate the false positive rate using by observing these two formulas closely? No answers to this? Yes, I got an answer. Yeah. When we closely see these formulas, they have similar terms in the denominator, and in the numerator they are separated by Tn and Fp. So when we take sum of these two, like false positive rate and specificity, so it is number of false positives plus true negatives divided by false positives plus true negatives, which is equals to 1. So that means sum of false positive rate and specificity is equals to 1. So when specificity is 0.75, false positive rate will be 0.25. Yeah. We have these last two questions for the day. Okay. So the purpose of the cross validation will be a technique that evaluate models performance using multiple splits of a data. Think a model has a 10 data sets, so it will train model. If you take leave one out cross validation, it will train model on 9 and evaluate its performance on 1. Likewise, this process is repeated until all the data points have come into the training set. Otherwise, if you take 5-fold cross validation, so it will take 5 training and 5 test. So, and this process is repeated until all the data has once comes into the training point. Next is, what is the purpose of k-fold cross validation? Is also they help to radius or variance, or helps us to understand the uh, variance, or how well the model can learn the error rate or error function in the process. So I'm done for today. If you have any questions, please turn on your mic and ask, or you can put up in the chat box. The Weka tutorial I'll be giving in the next class starting, followed by the overview of the course. If no questions, you guys are free to leave. If you have questions, please post it or unmute yourself and ask.